So yeah, hello everyone. Thanks also for the kind introduction, Matthew. So it's a pleasure here again to represent Bosch Research, I would say. And I want to thank Code Intelligence as well for inviting me to give this talk. Now, before I kind of start off and start off with my talk, I want to share you something interesting, kind of an event that happened early this morning. This is usually the time of the day where the time now, I drop my little one. She's almost hitting 2 years. I drop her off to the daycare. Today was a little bit different for her because my wife had to jump in. And as the little one was about to leave home with her mom, she started noticing me sitting in front of the screen and, staring at the screen. And all of a sudden, she started saying her favorite rhyme, which is said like, Old MacDonald had a farm. And I thought that was cute. I said, okay, bye. And started concentrating on the screen again because I was next in line. And now that they left home and the house started turning quiet, I'm kind of rethinking and wondering what that moment could have meant for the little one, right? So maybe she was thinking, work for daddy means listening to Old MacDonald on home screen, maybe. I hope not. Let's see. But anyway, if I were to rethink longer, that there could be other different interpretations that I could come up with. But keeping this pun aside, for a while now, I have rethought about the topic of fuzzing. And today I want to share with you why fuzzing needs rethinking in the context of automotive software. So with no further ado, I'll tell you how I've structured my talk. In this talk, I would want to mainly focus on sharing our experiences which we made at Bosch Research, basically in the last couple of years, while we have tried to apply fuzz testing in automotive software. So in a sense, I will walk you through these topics which you see, starting with the motivation. What are the different motivations to fuzz within the automotive domain? And then I will talk about some aspects that make automotive software a bit different. So these are also some of the aspects that's something I spoke about during the first con in September. And after covering these two topics, I will then walk you through this main core topic of this talk, where I will focus on why we need to rethink before applying fuzzing to automotive software. And this will be the main part, as I mentioned. And I will also share, going further, some thoughts on how we could rethink and finally wrap up with some conclusions and takeaways for you. Please note that this talk already assumes a knowledge of fuzz testing, so I won't be getting into the fundamentals of fuzzing, but I will instead focus on applying fuzzing for the automotive software. And as always, given the virtual nature of the conference, I encourage you to shoot your questions as and when they pop in your mind using the chat or the Slack channel of this talk. And if Matthew could help me picking some of the questions, that would be great. And I can hopefully spend some time in the end to go through the Q&A. So let's not have any further ado and get started. So firstly, why on earth should we fuzz automotive software? So there are different motivations for this. So if you see on your bottom right, there are different levels of automation. So where it starts getting interesting is from the automation level 3, because this is where the car as such takes more control than the user. And from 3 onwards, it's like the user is always coming out of the loop, right? So for software driving these kind of cars, it's very important that they need to have a really high assurance. And we see fuzz testing as one of the key technique which allows us to find these kind of subtle vulnerabilities as well as robustness flaws in automotive software, which are more or less about SAE level 3. And this is one of the proactive ways where we could say, hey, why not we fuzz this software continuously, like every night, and keep robustness, keep testing them for robustness. So one motivation in this sense is to be proactive and to take measures for continuously fuzzing automotive software. The next one comes from another domain, because fuzzing of late, as you've seen also in the introductory talk from Sergey, has been very effective in finding even subtle vulnerabilities in, say, Chrome browsers and other domains, right? So in that sense, it really makes technical sense to use fuzzing, because it can also be a part of the CI/CD to find as yet another effective way of finding bug hunting and security vulnerabilities. So this is the second way where you see that, okay, this technique is very promising and you can use it. So on this left side, you see mainly one is of the mindset where one is proactive. and one thinks that fuzzing makes sense, and we just do it. On the right side, there could be other motivations. The first one would be compliance. For example, there could be internal norms. A notable example here is from the Microsoft industry, where they, as a part of secure development lifecycle, already emphasize that fuzz testing could be one of the techniques that can be used in complement with other static analysis and things like this. And if we come into the automotive domain, there are future norms in the shaping now, such as ISO SAE 21434, which also highly recommend techniques like fuzz testing to be more or less used. So that would be one extrinsic motivation. And the second one comes from the customers themselves, where most of the manufacturers could emphasize that fuzz testing could be done, and basically that gets kind of enforced on you. So on this right side, what you see is that fuzzing gets more or less imposed, and you have to do it. So this is one, okay, I would say a reactive mindset, where you wait for extrinsic motivations for you to kind of roll down this fuzzing bandwagon. So there, all in all, there exists this intrinsic and extrinsic motivation. So where we stand now in automotive is that we have a mix of both intrinsic as well as extrinsic motivations. So when it comes to protocol fuzzing, there is already a high awareness that, and also requirements from multiple fronts. So to speak, there are extrinsic motivations for doing these kind of things, and even industry-grade tools. Whereas when we have to fuzz the API or the application behind the protocol, the motivation is at the moment more or less intrinsic. And here there are excellent and notable scientific community work and open source tools, and a lot of startups who are also engaged in this arena. So this kind of more or less sums up why we do fuzzing, and there are intrinsic and extrinsic motivations within the automotive industry to do such things. So moving on, the second topic, I want to focus more on like what on earth now makes automotive software a bit different, right? So here I will go through 3 of the differences one by one to show you how these differences can also create challenges for us going down the line. So the first one is a classic case where, you know, for most embedded software, that's that of platform dependence. So if you are aware, if you already know highly portable software, which is more or less in the IT or web domain, welcome to the world of embedded software, where the software is very highly platform dependent, or you could even say it's very patriotic. So what makes embedded software a bit peculiar, and what challenges or impediments arise due to such an entanglement with the platform is what I'm going to talk next. So coming to the peculiarities, you could see that there could, on one side, there is a really high platform dependence, because this is due to also the resource constrained nature of these embedded and IoT devices, where all the bits are more or less jammed into the last possible optimizations, and then try to put this on running on this hardware. So there's a really strong dependence on a particular hardware in this sense, and that's what's also uniquely characterizes embedded software. And in the second case, when it comes to automotive, there is a very predominant, in that sense, an established practice till now that hardware in the loop testing has taken off, and it's being kind of done extensively, right? So this also is very valid, because these kind of test environments are very representative when it has to deal with the timing of the actual hardware, of the functioning of the actuators and things like this. So I would say that's another a mindset question, how to move from hardware in the loop testing to somehow do it virtually, right? So that's the second peculiarity of this kind of embedded software, what we see. And the third one is more or less dictated by most of the safety norms these days, ISO 26262, which also heavily emphasize that all the critical components, such as the compilers, which can emit code, which then are used in safety critical devices, they have to be really certified. So we have, it's very customary to use certified compilers, cross compilers in our domains. So all these peculiarities kind of also create impediments, and some of them are because of this platform entanglement or dependence. It becomes more or less mandatory to stub the software, because software has to now be stripped off, has to be made sure that the hardware dependencies are encapsulated and then taken away to test it in isolation. So first thing is that the hurdle is to create this kind of stubs and fake devices and things like this before we start fuzzing. And the second problem is also most of the open source tools these days they work really harmoniously in a Linux or Unix-like environment. And to get an automotive software executed, stripped out and executed on a Linux kind of an environment is not so easy and straightforward, and it's not also possible out of the box. And another challenge comes when we see a really monstrous and humongous build chains, which are complicated, which involves code generation and things, and they require special treatment. One of my personal experience was that when we were fuzzing projects, we were trying to create fuzz targets, and we found out later that these targets which we created got kind of wiped out because the build chain was more or less rewriting the code in different stages. And this kind of also created a tricky scenario for us to get started with. And the last one is that if you look into conventional domain like fuzzing for file formats and things like this, they are, I would say, a bit easy to start with. But when it comes to automotive software, the interfaces itself are not so trivial. And this also creates a challenge in more or less creating fuzz targets in this case. So all in all, I would say in this fuzz difference creates a challenge where the entry barrier for fuzzing automotive applications is relatively higher. So this is the first one. And this also leads to, I would say, in that sense, a really high skill requirement when it comes to fuzz testing. That means to say that fuzzers these days are still more or less in the realms of experts, and they have to more closer to users as developers as we proceed to gain higher acceptance. Then let me focus on the second aspect now. The second peculiarity stems from the fact that automotive software is predominantly stateful. So what I mean by stateful is that a set of series transitions or state transitions have to occur even before something interesting happens. So this kind of creates interesting challenges because current state-of-the-art coverage-guided fuzzers more or less target software which with single inputs, whereas stateful programs require sequence of inputs. And when trying out the sequences to find a bug could be so long that mutations could become infeasible. And on the second side, we see that there is no adequate consideration for evolving program state during input generation. And lastly, it gets more or less tricky when software runs in an infinite loop. That's usually the case with embedded systems, and they have to be reset in an appropriate way to free up resources. So all of them create an interesting challenge, and fuzzing cyber physical software is still an open concern, as we've also seen in some of the academic conferences. Therefore, we see that we need also novel techniques to look into the domain and to fuzz stateful embedded software in the automotive context. So that's the second difference, which creates this challenge of finding unique techniques. And the third one and the last one is the one which is nowadays becoming more of a rule than an exception, because the software supply chain for automotive is becoming bigger and even complex. And nowadays, it's common to also integrate third-party software, which are often available as provided as binaries from different vendors. So such a setting makes efficient white box and gray box approaches difficult or even impossible. And we need to look for how we, and if you look into the impediments, it's also not easy to see. For example, the executing automotive binaries natively require also special emulators, which are not supported. For example, the emulators which are openly available, like Qemu, Unicorn, Gempi, they don't support the architectures which are microcontroller architectures which are used in the automotive domain. So we need also, in this sense, really scalable approaches to fuzz automotive applications and even binaries, and which is often a challenge. So this more or less finishes the first part where I talked about the differences. I have to note at this point that the differences here are not exclusive for the automotive domain. It is also likely that other domains in the embedded space, like even avionics, railways, or cyber physical systems in general, also exhibit these kind of similarities. Okay, so now coming to the main part of my talk. Why should we rethink fuzzing after all? So before we start to rethink, let's first look at and even acknowledge the areas where fuzzing excels today. So fuzz testing is efficient where, for example, we have in-house software which has to be analyzed, and there's a possibility to access source code. So this is the typical realm of white box fuzzing, I would say, which is also predominant in industries these days. In other industries where even Microsoft keeps doing these kind of fuzzing on a day-to-day basis. And the fuzzing community is also doing an is doing an excellent job in optimizing fuzzing in the second case, right? So this is also where fuzzing really works well, because there are really fine tunings available to create more efficient fuzzes these days, be it with orchestration, be it with grammars and things like this. So the community is more or less focusing on making fuzzers more efficient in this case, right? So, and lastly, protocol fuzzing has lifted off already. So there is already a commercial tool available, and also for these kind of fuzzing. And when it comes to software fuzzing, which are beyond protocol, we have a vibrant community of bleeding edge open source tools, mainly for software fuzzing. So these are the cases where we notice that fuzzing is really good in that sense. So all of these are valid reasons, but when it comes to applying them for automotive software, we seem to have witnessed just the tip of the iceberg here. Now, before us and underneath the iceberg exists a domain-specific problem which needs rethinking. And this is where I would say that beneath the iceberg also exist interesting problems which are specific to our domain. The first one is the case, as I spoke about, there is no homogeneous assumption that we always have access to source code, because there are also third-party binaries and so on. And going on, it's crucial to begin with to enable automotive software to start fuzzing. And then as a next step, it could be enough to even optimize it further. So I would say to begin with, it's really crucial to get automotive projects start doing fuzzing, and then throw all the other sophisticated techniques on these kind of software, right? And the third one is that the open source tools which are available these days, they are excellent, but they impose restrictions which only a handful of automotive projects satisfy. So in our experience, at least, if we take a bunch of 10 projects, there are just 2 of the projects which require minor reworks before they can be used, before open source tools can be used on these kind of projects, right? So this also, coupled with the previously mentioned differences given platform dependence, statefulness, and among others, create significant other challenges for us to start off with this fuzzing within the domain. So another example with respect to this domain specificity here is that you could imagine software is also not just built for a specific platform, but also for a specific operating system, which is real-time in nature. So example could be different real-time operating systems which are commercially available. And you could see that the open source tools in this case more or less assume that the software runs as is on Linux. And this is not the case, because our software in most cases would also be compiled and even using the APIs or the target APIs, the system calls of these proprietary real-time operating systems, which makes them all the more complicated to kind of strip out and port it to Linux in this case. So to summarize, I would say rethinking is now required, because automotive domain needs effective fuzzing to begin with that can address the domain-specific needs first, and only after achieving this, the efficient techniques could become more relevant. Okay, so now having made this statement regarding rethinking, I want to present 2 ideas about how my team is trying to come up with ways of rethinking. So I must, however, admit that these ideas are future work for our team here, but please consider them as more or less like a hypothesis which still requires some amount of validation. So the first one is the idea to rethink fuzzing in the context of software for cyber-physical systems. So typically you see here in the picture, a coverage-guided fuzzer will try to generate interesting inputs for software or even binary under test by instrumenting and sanitization techniques which are done on program or even binary level. And during runtime, such information which are pre-made available could be used to leveraged to use even the code coverage information and to mutate even existing inputs and even maximizing code coverage. And traditional fuzzing from the IT domain, or even the fuzzing for traditional software or even the IT domain, this happens mainly on PC, right? And for cyber-physical systems or even embedded system, the software has to more or less be running in a different kind of an execution environment, right? So the key idea here is to bring fuzzing and to introduce them into the execution environments where even automotive software or cyber-physical software runs. So this could be something like an emulator, which you see here. And there are really interesting research challenges in this arena. For example, if you think about cyber-physical software, which normally receives inputs from the environment, produces output for the actuators, and how would such a software, how to meaningfully create inputs for such a software and observe the outputs of such a software, right? So that could be an interesting question. And another one could be, could it be possible to more or less reduce the search phase for testing when with the information which is already available from the software in the loop environments or even plant or environment or the physics models? So that could be another interesting question. And the next one could be, how could events, or how critical could be the test results in the context of the system, right? So we could find some vulnerabilities, but you need to really understand the interplay of this particular vulnerability in different application stacks within the software in order to make an assessment also on the system level. So when it comes to binary, it could also be interesting to see what could be the sanitization techniques and all the things, instrumentation that could be done like in a retrospective manner for the binaries, right? So in this case, I would say rethinking is required in the context of cyber-physical software, and there are very interesting challenges. So to sum up, we need, going further, really systematic approaches to enable fuzzing for cyber-physical software, basically in our domain. The second rethinking is to more or less anchor fuzzing firmly into the software development process. Here, our learning is that one could really excel in building an excellent fuzzing platform. In doing so, for automotive, we more or less found some initial momentum, right? So we could say that we were somewhere on top of this hill, slowly creating momentum for this fuzzing topics. But to let the fuzzing ball roll down the hill, we need something else that is other than platform to push fuzzing also with sustained momentum. So the key to sustained momentum in this case is to mainly anchor fuzzing firmly into the software development process. As you saw also in the introductory talk, Sergey also mentioned about very well-established processes within the automotive system, how the software is developed in this V model, which slowly moves towards DevOps model now and things like this. So we need to make sure that to keep the momentum, it's also required not just to build platforms, but to make sure that the software and development process also adapts and even incorporates these kind of techniques as a part of their daily CI/CD, right? So making fuzzing a part of CI/CD and anchoring it firmly to become an integral part is a very important way to rethink also to keep the momentum going further. So with this, I'm more or less coming to the end of my talk. To quickly wrap up, I spoke about these topics for you. To begin with, I mainly told what are the different motivations, intrinsic and extrinsic motivations to fuzz automotive software. And I told three differences how automotive software is different compared to other software in the IT domain. So this leads to like high entry barrier for fuzzing. We have statefulness in software and even complicated build chains and supply chains for automotive, which includes binaries, which also complicates fuzzing. And when it comes to rethinking, I would put emphasis on the fact that we want more effectiveness for our domain, for fuzzing to work in our domain, and then we can talk about efficiency in the later step. And some ideas about rethinking is to think about what could be interesting research challenges for fuzzing cyber-physical software and tackling them one by one, and also at the same time trying to increase the momentum by anchoring fuzzing firmly into the software development. So in that sense, I would say cyber-physical software is probably the next frontier for fuzzing. Finally, some takeaways for you. So we have more or less created an on-premise platform. As I mentioned the word platform before, this is the platform that we created within Bosch, which not just uses vanilla techniques, pure vanilla fuzzers like AFL++, libfuzzer, but also builds on top of them to support grammar, to support statefulness, to have grammars, to have fuzz orchestration. And this we have built this in order to also scale for numerous projects within Bosch, what you see on the left side. So if you are a researcher working on cool advances of fuzzing for embedded software, you could more or less package your fuzzer in a kind of in a containerized format here in the Docker, and it could also be as well a bottle in our architecture, which is called Crate, right? So if you are interested in contributing, please get in touch with me. And I would say with this, it is more or less, this brings me to the end of my presentation. And at this point, I'm glad to take your questions. And Matthew, if you could help me picking some of the questions from the chat or from the Slack, that would be great.
Okay, actually, thank you so much for the wonderful talk. It's really thought-provoking. I particularly like your rethinking bullet points. I think those are really good areas for the community to focus on. So thank you very much for that. So for the audience, if you want to ask questions, please join the Slack community, and you can then find a channel for each of the talks. For that, you click the little plus icon in your channels view, and then you can search for the name of the speaker, and you'll find the Slack channel there. So we're getting lots of questions, so unfortunately we won't be able to get into all of them, so I'll pick some out. Apologies for those who don't get read out, but Rakshith, you can go into the channel afterwards and see if you can maybe answer some more questions then. Mm-hmm. So you mentioned kind of the open source community and some drawbacks of the current solutions, and Torbjörn is actually asking how much software used in automotive can actually be fuzzed with traditional fuzzers like AFL?
Yeah, so that's also the question we asked before we started fuzzing, right? So it's really difficult to give a percentage point here, saying this percent of software is clearly. What works really well in cases is where, for example, simple things like, you start with an automotive software, you somehow have a very good abstraction within the software where you can say, this software can be eliminated of particular compiler dependencies and easily run with GCC, right? So if you have such software, which in the first place compiles with GCC, I would say you have already had an entry point, because this is very easy to compile this kind of a software, get an executable and run it on Linux and start throwing AFL++, AFL, libfuzzer at it. So I would say this question, at the moment, based on my experience, I would say we are somewhere around 20 to 30% level here, to see, at least based on my experience, the percentage of projects which we encountered says that at least 1/3 of them could, with minor reworks, start using fuzzing. But for the rest, we need other solutions or different workarounds.
Okay, thank you. Then we have another research-related question from Paul, who asks, what research is currently active into fuzz testing embedded systems? So where do you go for cutting-edge information, Rakshith?
Yeah, so I mentioned one point because in this talk, I basically mentioned the three differences, how they differ. And in the FuzzCon in September, I also went through the solutions which my research team are working on to improve stateful fuzzing and things like this, right? So I would say in one aspect, we are already thinking about how to bring fuzzing into to fuzz stateful software. So that is one research direction. Apart from this, there could also be in the lines I mentioned in this talk, is to see how to bring also the fuzzing techniques into the execution environments where the software are running these days, because they use software in the loop simulations with plant models and environment models, with different kind of models that they work to interact with physics. And it would be really interesting to see from a research point of view, what would be the entry point for fuzzing in these kind of in the loop scenarios.
Yeah, okay, thank you. Okay, sadly, that brings us to the end of our time slot. There are lots more questions audiences have, and I have as well. So maybe, Rakshith, you can have a look in the channel
Sure.
and answer some more questions there.